Welcome back to AP Chemistry and General Chemistry. I'm Jeremy Krug, and in this video, we're continuing our discussion of acids and bases. Now, in this video, we're specifically looking at the concept of the autoionization of water and how there are hydrogen ions, or as we sometimes call them, hydronium ions, and hydroxide ions in pretty much every acid and base solution. Now, how do we get this? Well, there's this reaction that actually takes place in water. If we have a plain, pure solution, or I should say a pure amount of distilled water, we actually find that this reaction right here takes place, where what actually happens is some of these water molecules will actually react with each other. So you might have a water molecule here reacting with this water molecule. One of them acts as an acid and donates a proton. The other acts as a base and receives a proton. Well, what are the products? You're going to have these ions here, H3O plus and OH negative. So we're going to have that hydronium ion produced and the hydroxide ion produced as well. Now this is a reaction that does take place, but it does not take place to a very great extent, which means you're going to have a whole lot of the reactants over here. You're not going to have a whole lot of product. Now that tells us that the equilibrium constant for this reaction is going to be very small, isn't it? When a reaction doesn't happen very much, you're going to have a very small equilibrium constant. As it turns out, the equilibrium constant here is very small. In fact, at 25 degrees Celsius, the equilibrium constant for this reaction is about 1 times 10 to the negative 14th. So that's really, really small as far as equilibrium constants go. Now, this is a very important equilibrium constant to us. In fact, we actually give this a name, or I should say a letter. This is called Kw. Kw. Of course, that W stands for water, doesn't it? So this is the equilibrium constant for the autoionization, or we might call it autodissociation sometimes, of water, where we have H3O plus concentration times the OH minus concentration equals 1 times 10 to the negative 14th. So as you can see, we're starting to expand our alphabet of equilibrium constants. We had Kc, we had Kp, we had Ksp earlier in this course. Well, now we have Kw, and we're going to keep adding a couple of those, I should say, we'll add a couple more equilibrium constants to our alphabet here in a couple of lessons. Now, this equilibrium constant expression is very useful. In fact, we can use this to figure out how much hydroxide there is in a solution if we know how much hydrogen or hydronium there is in something. Or we can go vice versa. If we know how much hydronium there is, we can calculate the hydroxide as it says here. Now, I do want to point something out here. The H plus and H3O plus, these are basically interchangeable. Sometimes we write the equation like this. We could actually write it as H plus times OH minus equals, I should say, 1 times 10 to the minus 14th. The H plus and H3O plus are, for all practical purposes, interchangeable in AP Chemistry. Now, in upper level courses, you might find a slight difference there, but for this course, we're going to say it's basically the same thing. Now, let's take an example problem here. Let's say we have that the hydrogen concentration in a solution at 25 degrees Celsius is equal to 4.5 times 10 to the negative 5th molar. Calculate its hydroxide concentration. Well, we're going to plug into that equation that we just had here. We have H plus in this case, so we could use H3O plus, same thing, times hydroxide equals Kw, which is 1 times 10 to the minus 14th. And we're going to plug in the H plus concentration, which is this number right here, where it has H plus. And so now all we have to do to solve for hydroxide is take 1 times 10 to the minus 14th and divide that by 4.5 times 10 to the negative fifth. So when we do that, we get an answer of the hydroxide concentration equals 2.2 times 10 to the negative 10th moles per liter. So do you see how this works? If we have the H plus concentration, we can determine the OH minus concentration, or vice versa, using this equation. Now let's try another example. Let's say that a solution at 25 degrees Celsius has a hydroxide concentration of 5.3 times 10 to the negative 8th molar. Calculate H plus concentration in this solution. Well, we're basically just going to use that same equation again. We have H plus times OH negative equals 1 times 10 to the minus 14th. This time, the problem gives us the hydroxide concentration. So the hydroxide concentration gets plugged in right here, and we're going to do the algebra on this. So all we have to do, once again, is take 1 times 10 to the minus 14th and divide that by 5.3 times 10 to the negative 8. And when you do that, you get an answer of H plus equals 1.9 times 10 to the negative 7th molar. So hopefully you can see how this works. We can take one and figure out the other using kW's value, which is 1 times 10 to the minus 14th. Now, I'd like for us to introduce another concept, a very important concept in chemistry, one you've probably heard of outside of this chemistry class, and that's the concept of pH. Now, you probably have learned in maybe a first-year chemistry class, or maybe a biology class, or just some other, just from living, that pH is a measure of the acidity of something. And the lower the pH, the more acidic something is. Well, in chemistry, we actually have an equation for that. pH equals the negative logarithm, base 10, of the hydrogen ion concentration. So negative log of H plus. So what that means is, if you have an H plus concentration of 1 times 10 to the negative first, well, guess what? The pH is just that number right there. The pH is just equal to 1. And likewise, if H plus is equal to 1 times 10 to the minus second, then we can say that that number right there, pH is going to be equal to 2. And what about this? If H plus is 1 times 10 to the minus third, it's getting more dilute. Well, guess what? The less H plus there is, the pH keeps going up, doesn't it? So the pH would be 3 this time. If H plus is 1 times 10 to the minus 11th, then the pH is just that number right there. It's 11, isn't it? So we can just keep on doing this. Now sometimes we have H 1 times 10 to the minus 7th. Well, sometimes we have a case like this where it's perfectly neutral. You know, pH 7 is considered neutral. There are other cases where you actually have to plug this into your calculator. In fact, most of the time we do. You know, 2.3 times 10 to the minus 6, well, you're going to have to key this into your calculator and take negative log of 2.3 times 10 to the negative 6, and it should be about 5.64. Now, what if we have something like this? If we're given the hydroxide concentration, can we still find the pH? Well, we certainly can, can't we? We have to do that other step first and calculate H plus from that. So we'd have to do like we did in the last slide here. Take 1 times 10 to the minus 14th, divide it by 1.5 times 10 to the minus third, and we get that the H plus concentration is about 6.67 times 10 to the minus 12th. And then we take the negative log of that number, and we find that the pH is about 11.18. So some of these you may have a couple different steps if you're given OH minus and you have to convert that to pH. Now, when we talk about the pH scale, you might wonder how to go in the other direction. If we're given the pH, how do you find the H plus? Well, it's something called the negative antilog. And negative antilog just means this equation right here that you see on the screen. H plus equals 10 to the negative pH power. So if we have a solution that has a pH of 1, that means that the H plus is going to be 10 to the negative 1 power, which we can key into our calculator or just know that number. It's about 0.1 moles per liter, isn't it? If we have a pH of 3, well, that means that the H plus would be 10 to the negative 3 power, or 0.001 molar of H plus. How about a pH of 9.58? Well, once again, the H plus is going to be just 10 to the negative 9.58. Now, you're going to need a calculator for that. On your calculator, you probably have an anti-log button. If you hit second log or shift log, you'll see this 10 to the x button that pops up. And if you key this in, you can evaluate that number. It's about 2.63 times 10 to the negative 10th molar in this case. And what about pH equals negative 0.54? And yes, it is possible to have negative pHs. That means that H plus equals 10 to the positive 0.54 power this time, isn't it? Which is equal to about 3.47 molar. That's a very concentrated acidic solution, isn't it? If it has all that, 3.47 moles per liter H plus, very acidic, it can have a negative pH, as we can see here. Now, when we talk about the pH scale, this might be a graphic similar to what you've seen in a science textbook in your other courses, or maybe just you've seen this in a chemistry textbook or just in daily life. We know that pure distilled water has a pH of right around 7, so that's why I have this in here. The water is about 7, and it has very little acidity or basicity to it at all. That's why the numbers are small here toward the middle. On the edges, we have a lot of acidity, a lot of alkalinity here. So in the case of coffee, it's got a pH of about 5. Lemon juice is about 3. Coca-Cola is about 2. This hydrochloric acid is actually less than 0, as we could see in the last example. And things that are basic, things that are bases, tend to have a pH greater than 7. So you got your baking soda in maybe the 8.5 here. Things that are good cleaning agents tend to be basic. So we have hand soap is about maybe a 9 or a 10. Once you get beyond that, this is not something that these are not things you'll want to have on your hands for very long, like ammonia solution or bleach, and certainly oven cleaner. So that's just a very quick graphic of the pH scale. Now, whenever you have a strong acid, the H plus concentration is just equal to the molarity of the acid. Now, why is that the case? Well, that's because acids dissociate 100% all the way, don't they? So for example, if we have HCl, and we have this example right here, HCl, if it's aqueous, is going to undergo this reaction here. It's going to make H plus and Cl negative, and those are both aqueous. And notice that I have written this or drawn this as a single-headed arrow. It goes all the way. There is no equilibrium here. So if the concentration of the HCl is 0.05 molar, then guess what? The concentration of the H plus is also 0.05 molar, since this is a 1-to-1 ratio. Now, if we wanted to know the concentration of chloride, well, it would also be 0.05 molar, as we said in an earlier part of this lesson, right? So we're interested in the H plus. Well, it's got a concentration of 0.05. We just take the negative log of that, and we find that it's about 1.30. Same thing for the nitric acid here. We just take the negative log of 0.003. And when you do that, we key it into our calculator. It's about 2.52. Here we have maybe a little simpler example, because we can just look at the number there and say, pH is negative log of that number, which is just 5, isn't it, as we can see. How about perchloric acid? Well, we got to take the negative log of 12, don't we? It's going to be actually a negative number. It's negative 1.08. You can have an extremely acidic solution that has a negative pH like this. What about this last example? The pH of 1 times 10 to the minus 14th molar HCl. Well, you might think that we just take the negative log of that number and find that it's 14. But that sounds kind of funny, doesn't it? 14. 14 is a basic pH, isn't it? And that's not really what we have here. We have an acidic solution, but it's just so dilute. It's been diluted down with so much distilled water that it's practically all water, isn't it? And so we can say that the pH of something that's very, 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 very dilute, like this, is practically all water, and it's just 7. And the scientific reason for this is that we can say that the hydrogen ion or the hydronium ion that's present from the autodissociation of water is actually more prevalent than the hydronium ion present from the HCl. It's very, very small compared to what's present from the autodissociation of water. So it's just 7. It's just like water, basically. Now, let's take another scale here before we finish up the video here. And this is the pOH scale. Now, pOH is negative log of hydroxide. Hopefully that makes sense. If pH is negative log of H, then pOH would be negative log of OH, wouldn't it? So that means that if the hydroxide ion concentration is this, then that means that the pOH would just be the negative log of that, or basically 4, wouldn't it, as we can see. Or if the hydroxide ion concentration is 1 times 10 to the minus second, then pOH is just equal to 2, as hopefully you can see. Or if it's 1 times 10 to the minus 13th, then the pOH is 13. Hopefully you can see that. Or if the hydroxide ion concentration is 1 times 10 to the minus first, then the pOH is 1. So this works kind of like the other one did. If we have a case like this, where OH minus is, it might be helpful to put that into scientific notation, 1 times 10 to the minus sixth, then the pOH is just 6, isn't it? And of course, there are cases when you'll have to actually key this into your calculator. You actually have to break out that calculator and take negative log of 8.4 times 10 to the negative third. I'm getting an answer of about 2.08. So yeah, that's our pOH. And sometimes you got to do that extra step. If you're given an H+, you've actually got to take 1 times 10 to the minus 14th, divide it by this number, and get the OH minus concentration, which is about 1.33 times 10 to the negative 10th, and now take negative log of that number. It's about 9.88, somewhere in that neighborhood. So hopefully you can see how we get pH and pOH. Now, how are these related to each other? Well, the pOH scale is like the backwards version of the pH scale. So notice everything that we had here on the left that had a very, very low pH has a very, very high pOH. And the oven cleaner, I have this obscured unfortunately by my square up here, but the oven cleaner would have a pOH of about 0. The Clorox bleach would have a pOH of about 2. And if you actually start to look at all these, you'll see that the relationship between these is that the pH of a solution plus its pOH is going to be equal to 14, as long as we're at 25 degrees Celsius. Now, if you think about that, that makes sense, because we said earlier, for just as an example, that the lemon juice was about a 3 on the pH scale, right? And the lemon juice is about an 11 on the pOH scale. So that makes sense. Add them together, that's about 14. But I'm going to go one step further. I'm going to say that these two equations right here are actually the exact same thing. I'm going to put that out there just as a mathematical statement that, you know, H3O plus, or H plus basically, times OH minus equals 1 times 10 to the minus 14th, and that is the same thing as pH plus pOH equals 14. Now let's see how we do that. Well, there is just a very simple way to go from one to the other, just derive the second one from the first. I'm going to take the log of both sides of that equation, like this. And when we do that, we know that the log of any product is equal to the sum of the individual logs. Right? So this section over here is the same as log of H3O plus the log of OH negative. And the log of this number is just negative 14. So I'm going to just evaluate those right here. So we have the log of hydronium ions plus the log of hydroxide ions equals negative 14. Now I'm going to take this line, this equation that we have, and multiply the whole thing by negative 1. So I'm going to do that, and it's going to look like this. So now we have the negative log of hydronium plus the negative log of hydroxide equals positive 14. Now we learned just a couple slides ago that the negative log of hydronium is pH, isn't it? And the negative log of hydroxide is pOH. So guess what? It's the same thing. pH plus pOH equals 14. So, have you learned something in this video? If you did, please smash that thumbs up button and subscribe to my channel if you haven't already done so. Our goal here in this video is to have learned about the autoionization of water. We know that if you know the H+, you can figure out the OH- concentration in a solution and vice versa. We've learned how to calculate pH, we've learned how to calculate pOH, and how to convert from one to the other. Thank you for watching my video. This was a long one, but there's a lot to talk about in acids and bases. Hope to see you again on my channel where we can learn some more chemistry together.